When we're dealing with our areas here, from basically here on out, we just got done with the trig unit. And just about every single section that we do for the rest of the school year, we're going to have at least one or two problems every day that has something to do with what we just learned with the trig unit. What I mean by that is whether or not you're going to be using Pythagorean theorem, SOHCAHTOA, special right triangles, or something like that, those problems continually show up in just about every single lesson or problem set that we do from here to the end of the year. Also, I don't know if you read the window when you came in. You know how I've been doing the countdown for Mondays for spring break? Well, there's only 9 till the end of the school year. Mondays.
There's only 4 Mondays.
Fridays there's a lot more, but it's nice to see that there's just 9 Mondays. We have a couple Mondays off. Anyway, so I know that you guys have seen a lot of this. And what I want to do is kind of go through a list of a handful of these areas. And guys, what I'm getting at here is that just to start out with, you've got a couple of very, very, very easy formulas. And I know that all of you guys have seen all of these before. None of these things are terribly new or anything like that.
What is that?
Trapezoid. Circle.
What does that say?
So anyway, we're talking about parallelograms, and the reason why I left it as just a regular old word as the parallelogram is that I wanted to remind you that a lot of times you see parallelograms drawn like this. You guys okay with that? And what they do in order to figure out your areas is that you're multiplying two things together, and with parallelograms, it's just base times height. Now, I wanted to re-emphasize with you where bases and heights get located a lot of times in these shapes. For example, a lot of times in parallelograms, you might see a height drawn on the outside of the parallelogram. Or sometimes you might see the height drawn on the inside. It doesn't matter. They're both still a height. Okay? But what makes the height and the base, those segments, is that the height and the bases are the segments where the right angles are formed. One thing to remind yourself is, though, is when it's drawn on the outside, this dotted line is not part of this. So this is your base, even though this is the height. Okay? You'll see that drawn that way with parallelograms, and you'll see it drawn that way from time to time with, obtuse triangles. And I'll redraw that here in a minute when we talk about the obtuse triangles. Super common, nothing too crazy. I know that you've seen this, and so on and so on. Okay. Rectangles, you guys all know the area of a rectangle. Again, that is going to be base times height. That's base times height. Parallelogram is base times height. Square. It's base times height, but what do you know about squares? All the sides are equal, so a lot of times what they do with the squares, you can say it's base times height, but since those two numbers are the same, they usually say side squared. Okay. So a lot of times you'll see it written as S squared, where S stands for the side. Okay. I know you've seen it that way, it's just because the sides are always the same. The sides are, for the base and the height, they're both the same value. That's why they say it's side squared. Triangle. What's your triangle? Yeah. Base times height over 2, 1 bless you, base, 1/2 base times height. There's a bunch of different ways to write it. For example, when you have triangles, it's obviously going to be 1/2 base times height. That's how I write it out. I know some students write it as base times height divided by 2. Some people use 0.5 what I wanted to show you though is the 3 different triangles that you can get. And we'll come back to these guys. So you can have a right triangle, an acute triangle, or an obtuse triangle. And depending upon which one you have, it depends on how they draw their bases and heights. Obviously, it's a right triangle. Your base and height is where they form the right angle. We know that. It's pretty easy. If it is an acute triangle, more often than not, it'll be drawn on the inside. So there's your height, which makes this whole segment the base. And then when you have the obtuse triangle, a lot of times the height is drawn on the exterior of it, on the outside. And you get that dotted line out here, which means it's a segment that's not technically there. So there's your height, and then this portion here is the base. It just looks weird, but I know that all of you have done this, and it's not. So far, so good. I'm an idiot. That's okay. And I'm fine with that. Trapezoid. What does trapezoid look like?
I'm the coolest guy.
Okay. What makes a trapezoid not a parallelogram? Just one set of parallel sides. Okay. So your trapezoid only has one set of parallel sides. And remember, you could have a regular trapezoid or you could have an isosceles trapezoid. An isosceles trapezoid had legs that were congruent. A non-isosceles can just be whatever. Okay. Now, when you have trapezoids, these parts that are parallel are called bases. Okay. And it's interchangeable. It doesn't matter which one's which. It really doesn't matter. But inside, there's always going to be the distance between the two bases is always going to be called the height. Okay. Bless you. Well, look, think about the sneeze. So when you talk about the area of a trapezoid, you're using the bases and the heights, and you wind up with 1/2 the height times the sum of the bases.
I think I've seen that before.
You guys have all seen this before. Yes. Okay. What's wrong? Yeah, you just do 1/2 base times height. Or sorry, 1/2 the height times the sum of the bases. Excuse me, I was thinking of the triangle. And the height, remember, is just how far apart the bases are. Excuse me, let me go from there. Okay. Terrible? Which gets us to circles. Guys, I don't have that much here, but I want to make sure we get through all this, and I got a bunch of different examples of how the weirdness is going to look. I know that's where you guys are going. Area of a circle. Because a circle is actually defined as a set of points that are equidistant from the center. Okay. A circle is defined by a set of points that are all equidistant to a center. No, it's a set of points. If you have a line, if you're talking about this segment that are equidistant there, that's just a segment that's been bisected. There's just, you're saying 2 points with an endpoint segment. What would have to happen is that this would have to be a set of points that goes all the way around. That's where you get this from, where the set of points go through the whole thing. All points are all equidistant to that center. I know you're trying to be smarty pants there. No, I'm messing with you. But that's where you get the circle. The circle is defined as a set of points through which everything is equidistant to the center point. Now, a circle is also something called a conic section. You guys ever heard of that before? They call it. A conic is if you take a. Can I see this for 1 second? This is perfect. This is a cylinder. You okay with that?
Yeah.
Now, what's that? If you take a cylinder and you cut it different ways, obviously not going to cut this, but if you cut it on different edges in different ways, you get different what are called conic sections. Obviously, if you let me make sure this is close. If you cut it square, you get like right down the middle of it, you get a circle. Okay. If you cut it on an angle, you wind up with ellipses. If you cut it going the other way, you wind up with things that are called hyperbolas. Those are the ones that have them going two curves going opposite directions. You cut it one way down the middle, you wind up with a parabola. It's a singular up like a cup or down like a round type thing. Actually, they can turn left and right as well. So those things are all called conic sections. A circle is a conic section. Now, with a circle, every one of these guys has this segment here. What is that called when it goes from the center to the side? It's the radius. Now, the radius inside of a circle, what do you know about all the radii in a circle? They're all equal. Very good. The radius of the circle stays constant. Okay. Now, also when you have a circle, you get something that goes from one end through the center to the other end. It starts with a D, and it's called the diameter. The diameter is technically, we haven't heard this before, it's called a chord. Okay? And we'll talk all about that stuff when we get to circles later on, but a diameter is what they call a segment in a circle that's called a chord. A chord in a circle has endpoints on the circle. Diameter is just the fanciest one. It's the largest of any circle. Because everywhere else, if you have a diameter, they're all short until you get to this one spot that it ends on the circle. So this right from this point to here, that's still technically chord, but we're not there yet. We'll get to it. I have a whole chapter on circles. We'll get to it. Now, yeah. Now, when we're talking about the diameter is made up of what? Two radius. Yeah. The diameter is made up of 2 radii. So if I double the radius, I get a diameter. If I take the diameter and cut it in half, I get a radius. Well, you know that. I mean, a lot of these little things, I know you know, I'm just rewriting things through. Now, when we talk about the area of a circle, that's always dependent upon its radius. And then this little thing called pi. You know what pi is for? Now, pi comes into play when you start talking about something called the circumference. You guys know what circumference means?
Yeah, I remember.
Working your way around a circle. Now, what happens here, and where all this pi and all that comes from, if you take a circle, and you give it a radius of 1, okay, if I take a circle and give it a radius of 1, if I start at 0 and go all the way around, how many degrees is that? 60. Very good. If I start at 0 and I go halfway, if I start at 0, I just go 91.
What's happening?
You like this all day? I'm sorry. Many of you guys have more classes. Now, when you're working with the circle, when you're talking about this idea of going all the way around in terms of degrees, you go around 360 degrees. If you are to walk on the circle, you're walking a distance. It's like the perimeter. The perimeter is called circumference when you're dealing with the circle. Now, what's that? Because of the Latin word circum, it's part of the circle goes around, something that goes around a distance. Meter. Anyway, so if you have a radius of 1, your circumference was 2 pi times the radius. So the circumference standardized as a circle is always 2 pi. Yes, ma'am? I'm just explaining where the 2 pi comes in. Okay. 2 pi is the basic to take you from 0 to 360 to get around a circle. It's 2 pi revolution. It's called a radian. Yep, that's what I'm getting. What happens here is that you guys remember on the calculators I told you to always make sure you're in that degree mode? You know how there's a mode in there that says rad? That rad mode is technically what they call radians. And what you're talking about there in terms of radians is when you're talking about degrees in terms of pi. And that comes from circumference. So what happens here is if you go 360 degrees, you go 2 pi. If I go 180, well, that's half of 360. So what's half of 2 pi? It would be 1 pi. And what would be half of that? 1/2 pi, pi over 2. Here would be 3 pi over 2. Okay? Because it's 1/2, 2/2, 3/2, 4/2. We have. Now watch this. What's half of 90? 45. So if I count by 45s, here's 45, 90, 135, 180, 225, 270, 315, 360. No, I'm showing you why all this works. Guys, watch. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 sections of 45 degrees to get around a circle. If I know that 45 degrees is half of 90, what's half of a half? A fourth. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, as you go all the way through. What happens here when you start talking about this when you get to algebra 2, everything goes away from the idea of degrees, and we switch them into terms of pi. These are called radians, and it deals with circumference. And that's what I just wanted to show you why we talk about circumference in terms of 2 pi, because you're breaking it down from a degree measure to what's called a radian measure. And that's how everything gets calculated out. Now, when you get to algebra 2, you'll do this stuff for a month, at least. Trig stuff is huge in algebra 2. Anyway, back to circumference. We know that area was pi r squared. And we know that circumference is 2 pi r. What's another name for 2 times radius? Diameter. So sometimes you'll see your circumference written as pi times diameter. And one of the things I just wanted to let you know is when you're using your calculators, this is one of the other big reasons why we kept saying use that multiview, is that it will always leave your answers in terms of pi. So if you have a radius of 4 and you want to find the area, you type in 4 squared and press the pi button, and it will actually give you the answer as 16 pi. It gives your answers in terms of pi, which is technically an exact answer. It's kind of like when we were doing their stuff with the radicals. You know, square root of 8 is 2 root 2, things like that. The calculator did that work for you. It got rid of the radicals in the denominator. It keeps things in terms of pi. It gives you those exact values. So if you're using the calculator correctly, you'll see all of that. Also, if you don't have that calculator, you know you're going to have pi in your answer. You could just quite literally, if your radius is 4, you know 4 squared is 16, so your answer would be 16, and just put pi next to it and call it a day. Units. Yes, sir. No. You'll never, in geometry, you'll never have to worry about it being radian, though. And quite honestly, very rarely will ever use radian mode, even in Algebra 2, because a lot of times when you get to when you use radian value, you're going to be able to get those answers because of your special right triangles. So, and that's where everything comes back to. You have 30, 60, 90s, and 45, 45, 90s. And each of these, let me go back to here real quick. Each of these spots, 30, 45, and 60, this value here is reflected here, is reflected here, is reflected here, and here. And it just changes the sign, SIGN, for the different quadrants that it lands in. So you won't even be using a calculator when you get to stuff like that. Okay. Yeah, this is just pressing buttons. Oh, I know. What if you had to do this? That's a really badly drawn semicircle. How would you find the area of a semicircle? What's that? Yeah, it's pi r squared divided by 2. Oh. Yeah, when you type in your calculator, what's weird about formulas, when they put formulas together, they put the value of pi or radicals or things like that. Those usually always go in front of variables. Now, when you type it in, you would type in 9 squared pi over 2. And that calculator will probably spit out 81 pi over 2. And that's fine. And then you put units, something squared. Areas are the one thing that I'm usually pretty much of a stickler, shall we say, when it comes to making sure you label. Always make sure you label your areas. Whether if you use units squared because you didn't read what it was, or you go back to make sure that you know it was meters or inches or feet or whatever it might be. Okay? But that's what it would look like. And again, I know that all of you guys have done these types of problems, and it's not going to be all that difficult. What's going to be difficult and or weird is when you have to put things together. For example, wrong one.